So we had like argument. Okay, it's visible. Theta, let's say in RD, and you wanted to minimize like a function f theta, right? Then we saw that you could look at the you could form this update. So theta t minus, I'm going to use gamma now for the step size, gradient of f evaluated it. The previous, like, or the current estimate theta, and then I take a step in that direction. So I take a step in the direction of gamma. Yeah, so it's a step in the direction, sorry, a step gamma in the direction of the negative gradient. So I added to theta t, and then I get t theta, theta t plus 1. And we talked about why this is reasonable. Anyone remembers why this procedure is reasonable? If I want to minimize f theta, what this gradient is an update is doing. So suppose I have like something like that, that would be if
taking the step in the largest decrease in that direction.
Yeah, so we discussed that if you think of just to reiterate f theta, I can expand near, let's say, the current estimate if you want, any point basically, in terms of a linear function. So the derivative really is a linear approximation. So if I have, let's say, f theta t plus h, it's the current value plus the inner product, or I can write it as f theta t transpose times h. This is basically the gradient of f at theta inner product with h. This is the linear function part. And plus O of h, this is going to 0 faster than h. So locally near the current estimate, if you can imagine that this h is going to be small, h is going to be a vector. The function really is linear. And so h is going to be my increment. So I'm going to add h to theta and move in that direction. In order to minimize the function, I'm going to minimize this linear term. Okay, so I'm going to move along the basically the linear function. And this is minimized if I move in the direction of the negative gradient by the Cauchy-Schwarz argument. Okay, so this is maximized if I move in the direction of the gradient, minimized if I move in the negative direction. So like intuitively, what happens is that I'm at this point theta t, and then I would have this linear approximation to the function. Okay, so that passes through this. So if you imagine that the point here is the origin, then the functional form of that line would be this second term. Okay, what I'm going to do is I'm going to minimize this. So if I minimize really, I'm going to go to negative infinity all the way, right? Because the minimum of this is going to go to, but I'm not going to go all the way. I'm just going to take a step in the direction. And here, like in univariate case, the direction is on either this side or this side, right? So there's like a sign to the direction. Either I'm going to move left or right. The direction, just like I'm going to use this line to determine whether I'm going to move left or right. The size of the step is going to be determined by this, and also the norm of this. But the norm of this can be absorbed into gamma. So you can think of the direction as really being gradient of f theta, f divided by the norm of this. So you can think of this as the direction, because this has unit norm. Usually you normalize. And then this multiplied by the norm of f at theta t. And then gamma, this whole thing would be another gamma prime. So this is really the direction of the gradient, or negative direction. And then the step that I take includes the size. So I don't have to worry about, I just care about the direction of it. Okay, so here the direction would be, so in what direction should I move? Left or right? Left, right? So the derivative, actually, if you evaluate it, so this derivative of this would be, the gradient here would be 2 theta. So this theta t is positive, so the gradient is positive, it's pointing towards the, is it positive? Yeah, so pointing away, so I have like negative gradient would be this. So pointing to the this side, okay? So I'm gonna move a step in this direction, I'm gonna end up here. At this point, another line is the best linear approximation. Again, this suggests that I have to move left, right? And I'm gonna move another like point here, and then it's gonna flatten out, right? So in order to understand this better, what happens if I take a very large step? If I take a large step, this approximation is not good, but it turns out that in this case, it might work. So if I take a very large step, so at this point, the gradient suggests I have to move this way. And let's say I take a step too much, I'm gonna end up here, right? Now, the approximation is gonna be like that. Oh, this is nice. Here's, okay. There's a ruler here. You guys can see it, but okay. Let's see. Perfect ruler. So there is this line. Now the best linear approximation is that the gradient of function is like the slope of that, basically, like up to the direction is the slope of that. It is pointing towards the origin. So here's it's pointing that I have to like have to move in this direction. Okay, so the gradient is still pointing towards the correct location, even if I did a bad job of taking a huge step. So if I now take a small step, it's fine. I'm gonna like do this, but if I take another huge step, I'm gonna end up like on the other side. This points me to this direction and then back. So you get a zigzag. You're not gonna like monotonically go. You're gonna like move too much and then overshoot, and then come back. Does that make sense, sort of? So this is the idea of gradient descent, is to do a like small step, but the step size matters, sort of. So what happens if I take a very huge step? Overshoot. In this case, I'm gonna always come back, but I'm gonna assign a homework problem later. So for example, if you have something like that, say something like this. Yeah, this is going to work as well. So for example, the easiest thing to see why sometimes in this case, like the fixed step size is actually not going to work. So at this point, the best linear approximation of the function itself, right? If I take a fixed step size, and if it's too big, I'm going to overshoot here, right? Like, let's say, and then I'm going to move back here and then back here. So I'm going to get stuck. And sometimes if you do like large step size, you're going to go to infinity. You're going to see that. So if you understand the linear approximation, you have to make sure that you're like taking a small step, and the exact step size is not so obvious. Okay. So sometimes you're lucky and a fixed step size sufficiently small would give you convergence. Sometimes you're even more lucky, and even if you do overshoot, like you take a bigger step, you're still fine. But it's not going to always happen. Okay, so that's the idea of gradient descent. And the reason why we talked about this is because we talked about the ERM. I'm going to come back to ERM, empirical risk minimization. But let's see like some of the mechanics of this in action, and then come back and do the ERM again. So is this clear, sort of gradient descent? Okay, so let's try. Right, okay, so if you have seen Python, you can sort of import these like packages. And so torch is the PyTorch package. In this matplotlib, this is like the plotting, usually one of the common plotting packages. So you say import this as plot, and then this module like is accessible. So I can do, for example, like you can say plot and then plot stuff. Okay, so you do this. If you do, so this basically renames it. Instead of saying matplotlib, that I can do this as well. Probably not here, but if I import it, I can do like plot, but because this is too much, you do that. This is like a mnemonic for this. Import torch. Torch is going to be accessible like it is. Usually people do this. I can do a tensor. So we'll do this. So that's that. And then I have some sort of a written here is like a little Python sort of script. You can write your own script and define your functions and then like work with this as a module. So I may come back to this, but I'm going to share this. This is actually basically what this Copilot wrote. So you give it instructions and helps you, right? So this plots the contours of a function. It doesn't matter, like the details for us is not as important. What I'm doing here is saying that from helpers, that's my module that I wrote, import everything. So now I don't have to write helpers dot whatever. I can just like call that plot contours function directly. So this is not advisable in general because it just pollutes your namespace, but because the functions are the ones that I wrote and I'm just easier for me to call, I'm going to do that. So this is like a basic format of trying to import packages or modules into Python. You can write your own module, basically just put everything in a py.py function, and then you can sort of import it and use your functions. And this is like a Jupyter notebook. I guess you guys probably are familiar, but you can do like interactive operations, right? So I can do 2 + 2 and then run it, it gives me 4, right? So you can easily like do calculations and see the results and move on. It's similar to what, like R sort of, in R you could do similar things or like R markup, but it's just these notebooks are very common in the Python sort of community, and it's helpful when you want to test things. Okay, so far so good. We're on board. Okay, so the first thing that I want to do is there's also another package called NumPy, which is for numerical calculations with matrices and arrays, and this goes hand in hand with this PyTorch. PyTorch is basically like a package that has this machinery that takes the gradient for you, so automatic differentiation. So you don't have to worry about calculating gradients by hand. And there's also a lot of like functionality of deep learning is built in, which is useful. You can also use NumPy, so these go hand in hand. I can, for example, generate random vectors or random matrices from in NumPy. We'll see maybe, but just remember NumPy as well. Oh, maybe. Okay. This understands a little bit of English as well. Okay, so what I want to do is like create a so the basic data type in Torch is a tensor. So here this creates a tensor, which is tensors are basically like generalization of matrices or vectors. But vectors, matrices, these are also tensors, but you could have multiple dimensions, like a cube of not like a number. Like you have 3 dimensions, 4 dimensions. So an array of multi-dimensional array of numbers. So this one is basically, if I run it, you can see it's just you can do shape. You can see the shape. It's just a vector, basically. Size is 2. If I do, for example, matrix, like 2 by 2, you get the size is 2 and 2. So this is just has one dimension. It's, let me just do this. There's a data type. It's like a floating point data type. And this is needed for doing gradient operations. So if you define it like this, for example, you're going to run into issues. This would be, as you can see, like only tensors of floating point and complex D type can require gradients. Okay, so like if you had this issue, just make sure that things are, you can either do this or you can declare the data type here implicitly, like explicitly. So this is implicit, but you can also do, I think, let me do this, just a bit of, again, PyTorch. So I can do like, I think, double, for example. Torch double. Yeah, that would be float 64. And do float 32. That would be float 32. Yeah, so that either that or let's just like more explicit. But the main thing is this requires grad is what tells PyTorch to keep gradient information about or stored in this vector. We'll see. So when I define it, I set requires grad to true. And you can also like check, for example, this has a property now that tells you that I can like, when you do dot, you can like access properties or function like methods. This is a property, it says true. So this is a tensor, like PyTorch tensor of type float 32. It's like floating point, basically real numbers, like with approximations, and requires a gradient. So PyTorch keeps tracks of that. Okay. So far, so good. Okay. Then I define a loss function. Okay. So here, so in Python, unlike R, the indices start from 0. So if I want to like access the elements of theta, the 0th element would be 1. And you can see this is also a tensor, actually, like a univariate, like a tensor, like scalars are also a tensor. And the first element would be 2. Maybe I'm going to do 2 points. So you can see the first element is 2 point. The first element is really the second element, okay? The 0th element is the first element. So here I'm defining a loss, which is just obtained by this operation. Theta 0, this double, this thing is just power to the power 2. And so that's how you take things to the power. So this is basically, if I want to, so this is like loss is equal to theta, let's say 0 squared plus theta 1 squared. Okay. So that's maybe mathematically, this is a function of theta. But you can see what it's doing is just computes the this value, and then you can print it. The loss would be 7 point. Let's do simple. Like do 2 here. So if I have 2, this is going to be 1 plus 4. It should be 5, right? Right. So it's 5. 5 dot, and you can see also it's this floating point. And there's this grad function. You can see like implicitly, PyTorch is keeping track of the gradient. The gradient is sort of a mapping, basically like a functional. It's going to be a function basically applied to any value for. So at this point, if I change value of the theta, or like, okay, not change the value. So, okay, so this is loss, okay? Let's not complicate things. Don't worry about this function. How do I take the gradient of this loss with respect to this theta? There's this operation, which is take the gradient of loss with respect to theta, okay? So this tells you that I have to do loss backward, right? And what it does is that it operates on this loss function and calculates the gradient of this loss with respect to whatever tensor that went into constructing it, and for which you required grad. So now this this guy knows what I should print next. That's like the artificial intelligence part. So this is like a little bit confusing because you call this function backward, or this method backward on the loss. It goes and calculates the gradient of this with respect to what? With respect to whatever you use to calculate it. So here we calculated loss based on theta, right? And we required gradient on theta. So PyTorch knows that when I do this, it's going to go calculate the gradient with respect to theta of this loss function. And it's going to store the gradient of the loss function with respect to theta in theta itself. Okay, so in the property, which is grad on theta. Okay, so theta will have a grad property. Originally, let me show you. Originally, there's no, if I try to show you the grad, there's nothing, so it's none. So if I print the grad, there's a property, but it's none. And none is like, none is basically null in Python, like empty. Once I do this calculation, then you can see that there is something in the gradient, and that's basically the gradient of the loss. So if you take the gradient of this, it will be 2 theta naught plus 2 theta 1. You evaluate it at this point, right? 2 theta 1. Should be evaluated, or so you understand what the gradient, right? What is the gradient of this guy? So let me show you here. So gradient, so if I have the loss, L theta is like theta 0 plus theta 1. The gradient of the loss, should have called it F. So this is like partial with respect to theta 0 and partial with respect to theta 1. So what will be the gradient? 2 theta naught and then 2 theta 1. So if I evaluate it at theta, which is equal to 1 and 2, what do I get? Yeah, so I should get 2 and 4. Right, so let's see. Yeah, so we got the 2 and 4, right? So this operation is pretty interesting, you will see. The reason why it's called backward is because it's like the backward pass in the neural network. Hopefully we'll see in neural network terminology. When you compute the function, it's called the forward pass. When you take the gradient, it's called the backward pass because of the way the chain rule works. It doesn't matter the name. It's just remember that this takes the gradient. Like it takes the gradient of the loss, or like whatever function that you put here doesn't have to be loss. I could have called this anything, right? So I could have called this fun, right? This is fun, sort of fun. And then I could have done fun here, and then you could see that the gradient goes back like that, okay? Sounds good? Yeah.
So this only works because your loss is defined purely on theta, right? Like if you made a mistake and wrote like some other vector and theta plus theta 0, it wouldn't work.
Can you tell me, for example, a mistake that I can do, see what happens? So you wanted to do it based on a different?
Yeah, like if you by mistake, instead of theta, when you use the others, like, I don't know, like another vector is second element, it would not work.
Can you think of an example we can try? I don't know what exactly would happen, but.
So let's say we make another vector called theta 2, and we say it's equal to torch dot tensor, and we can use the same elements.
Okay.
And then
So
and then instead of theta, when you compute the loss, instead of theta 1, you could just write theta 2.
okay, so we made this mistake. Stole that, and then if I do that, so element 0 of tensors does not require grad and does not have a. So the error is okay. So that's the error, right? And the reason why there's an error is because this guy does not require grad. So we didn't ask for theta 2 that requires. So this is false. So it cannot take, right? If you had like required grad on this, it would have worked. The grad property of this would contain the gradient then, right? You can think of like more complicated mistakes, then we'll see what happens, right? But yeah, generally speaking, this is going to take the gradient respect to all the tensors that went into constructing loss and for which you required grad. For example, if okay, so maybe let me do this. Right, and then do plus, so this is going to be theta 0, and then plus, for example, theta 2, 0. Okay, let's see what happens here. So we have a tensor theta that requires grad. We have one that doesn't require grad. And then the loss is like a function of both. Right. Okay, it takes the gradient still, right? And it's fine. Right. So this treats this as just a scalar. Right. So even if I do like the third, oh, something funny happened. Let's go back. Theta. Okay, still correct. We do this. Why do we get this? That's why the gradient is moving here. I can tell you why it's moving, but that's okay. Let's do it like this works so far, right? This is okay. If you rerun this, I cannot rerun this, but I have to recalculate the loss. And then it keeps adding to the, you can see the gradient is going to be like, and although the theta is not changing, this is one of the features sort of, which is also maybe a bug, depending on how you want to understand it. When you apply this backward, it calculates the gradient and adds it to whatever was in the grad before. So every time you call this backward, it's not going to reset the gradient. So whatever grad property of theta is, like whatever they would hold, it just calculates the gradient of loss with respect to that theta and adds it to the gradient. Okay, so if you want to get the real gradient, you have to zero things out. We'll see. You have to zero out the grad property to not have this accumulation. So it's designed this way because it helps certain properties. Yes.
Theta, and theta 2.
Yeah.
You use a loss function on both.
So that's the interesting part about that. So here, the theta here, we require gradient on it. So you can think of this now as a variable, optimization variable, right? This one is another PyTorch tensor, but doesn't require grad. So if you look at the theta 2, that requires grad. This is false, right? So this is treated as just like a fixed tensor. So it's not a variable. So when I construct a loss, you can think of this as like it's a function of all these, but these are really optimization variables. This is just a constant. So when it goes and calculates the gradient, it's going to take the gradient with respect to all the optimization variables. And so it's just going to populate the grad property of theta, right? Yes.
What is the theta now and theta one? It's like each of them is a tensor.
These are the coordinates of this theta, right? This theta you can think of as like a two-dimensional, like not two, length 2 vector. Right? Theta naught would be the first element, theta, the other one would be the second element, but they're really tensors. So if you think of the theta naught, if you do it, you can see it's just a tensor, but has one element, right? Theta 1 is another tensor, has one element, just the second element of, so theta is a vector, 1, 2. You pick the element 1 or element 2. And you can also look at the shape. The size is empty, so it's like really scalar. So if size was like, the size of theta is like, this is a vector. So if it was a matrix, for example, it would be, for example, I can define A to be, well, actually, this understands that I want this. Okay, good. So this is a matrix. How you define a matrix? So a list of lists. So 1, 2 would be the first row. The second row would be 3, 4. So that's how you define. And then the shape of this would be 2 by 2. Okay.
Then what's the difference between like, what if we just like define the first element to be 1 and 2, just be a scalar?
The first element be 1 and 2. What do you mean?
Why do we need to like construct this tensor?
Because I want to define a function which is see this okay. So I want this function. I want my loss to be, this is going to be my loss function, right? This thing is going to be my loss function. So it's a function of a vector, right? So L of basically theta naught, theta 1 is equal to theta naught squared. It's a bivariate function. That's what I'm doing, right? You could like have a scalar function. That's fine. So you could have defined like L of theta naught squared. That's fine. But this function is from R to L is from R2 to R. So I'm going to minimize this. Okay. So what is the minimum of this function? 0. Okay. So hopefully the gradient descent, and then the gradient is 0 at 0. You can see if I set the gradient to 0, the only place where in which it is 0 is 0. So let's see if that actually works out. So, okay. So this was the basic debate. The main idea is this backward operation. Now I have defined a loss, right? So if you think about this loss, this is how you define a function in Python, if you remember. And it just returns this value. It takes a theta and just calculates this loss. Okay. Now it's just really a function. And I have that plot contour that I wrote. It plots the contours. It doesn't matter what it actually is, but that's like the contours of the, it's a little bit too big. That's fine though. Yeah. Okay, you can see the contours, right? The contours of this are, these are the level sets. It's a level sets of this function are circles. So you think of the, so the level sets are, if I set it equal to a constant, so theta 0 plus theta 1 squared is equal to a constant. These are the level, okay. Yeah, go up, sorry. So if I define the set of all theta such that this is a constant, so let's say this C. There's like a C here. Let's call this lev C. So for different C, so if I fix C, the set of all points for which the loss is equal to C is one of the level sets of this. And the contour plot is just showing those level sets. Okay, so if I fix C, this is going to be a circle, the location of it like a circle. And if I vary C, the circle changes. So these are those, and you can see like the color shows you, these are like the blue is like a lower value, the red is a higher value. So if I do, for example, 6 is probably going to be a little bit, yeah, it's going to rescale, it doesn't matter. Okay, so let's now do gradient. So what happens is the gradient is going to be always perpendicular to these level sets. So at each location, the gradient is going to be pointing away, and the negative gradient points inward. Okay, it's easy to, like, if you remember the linear approximation. If I move on the level set, the function doesn't change, so that linear function is sort of zero. Basically, the direction on like tangent to this is perpendicular to the gradient. So these are perpendicular, and the direction which is perpendicular to this is actually moving in the direction of the gradient. The gradient would be like this, pointing always to the origin. So you're starting from every point, there is one direction that moves towards the minimum, and so you can see very like geometrically that you have to go to the minimum. The gradient set has to converge, most likely, if you don't do any crazy thing. Okay, so how do we do gradient descent here? Here's a simple way of writing this. So I start from some, let's say 5 point, like this is a point that I'm initializing. So I'm calling it data here. It could be theta. So let's call this maybe theta. So theta is this is the initialization. There's this learning rate, which is that gamma, the step size, number of steps 10. This is gonna keep track of the loss. So I'm doing this is the numpy 0. So this is gonna be a vector of size 10 that's gonna store the loss for us. And then I'm gonna do a for loop. So I in range of n steps is gonna like create a range from 0 up to like n steps minus 1. So it's like it's like in R like 1 up to n steps. It's just gonna be from 0 to n step minus 1. So what I'm gonna do is that first calculate the loss. The loss is this function that we define, right? So I'm gonna apply the current value, like apply the loss to the current value of theta. I'm going to store the current value in that vector at position I, and this item is going to extract the value. The loss is going to be a tensor, right? So if I can show you. So the loss applied to theta is going to be a tensor, but if I do the item, it just extracts that number. Okay, it's going to be a number. That's how you can extract it. It's no longer be a tensor. So it's just a simple way of extracting the scalar value from scalar tensors. So this is going to just store the value of the loss. Then I'm going to call this backward on the current loss. This is going to calculate the gradient of the loss with respect to theta and stores it in theta.grad. Okay, so this is going to be theta.grad. I mean, forget about this part. So this is really the gradient descent. So theta.grad is the direction of the gradient. I'm going to multiply by learning rate and then subtract it. So this is really theta minus, theta is going to be equal to theta minus learning rate times theta grad. This is the gradient step. Okay, because of this, we have calculated the gradient at the current value theta. That's my gradient. I'm taking the negative step and then there's the theta. And this is going to be new theta. So this is going to give us an error because of the like weirdness of PyTorch, but this is going to work. This is in like, it's like C++. In Python, you could do like in place This is just going to subtract this side from theta and stores it in theta. Okay, that's the same thing. So that's the gradient descent. And then we are going to zero out the gradient. As you can see, or we saw, if you don't do this, the next time when you call backward, it's just going to add whatever was to whatever was there. So you zero it out so that next time you calculate the correct gradient. Okay, so that's the gradient descent. If I run it, you can see there's this nice drop. I'm plotting the loss, like history of the loss. You can see it's just going to drop. Okay, so is this sort of clear to people how you do gradient descent? Okay, sounds good. And then I'm gonna also keep track of data. So show you how the beta varies. So we're going to create a beta, a list of betas, and so this is how you define this in Python, right? And then this is exactly the same thing. So the current loss is calculated. I'm going to store the current loss. I'm going to take this is calculating the gradient, take the step in the gradient, the direction of the gradient, zero out the gradient. Now I just have to call everything theta. Sorry. Theta list, theta, this one is going to be theta as well. Theta, here's going to be theta. And I'm going to append to this list. So whenever you have a list, there's this thing called append. So you can append whatever you want to the end of the list. What I want is the theta, but I'm going to apply the clone. So you have to clone it, because otherwise it's just going to store a pointer to it, and it's going to like keep pointing to this, the current value of theta always. So clone means like make a copy. It's going to make a copy and it stores it in this theta list. So if I run this, hopefully, let me do theta list outside so that you can see what it does. So this runs, and then you can see like the theta sort of starts to decay, right, towards zero. And here I'm just gonna maybe show this to you and then tell you what this is. Okay, theta tensor should be theta. Okay, theta tensor. So this is just plotting the thetas. Okay. Let's go start from 3, for example. Okay, we start. Okay. Okay, so we started at 3. So you can see that that's the initial point, and then one step takes me here, another step takes me here, and so on, and we move up to not the origin. So if I do more, it's like do 50. You can see we get very close to the minimum, and you can see we're moving perpendicular to the level sets, right? Sounds good. So why you're slowing down as we move towards the
gradient decreases.
The gradient decreases. So the gradient is going to be 0 here. So although you're taking the like a step size which is fixed, because the gradient gets smaller, you get decay like that. So that's gradient descent. Okay, very simple. So hopefully now you can like do deep learning, right? One step from this to deep learning. Just you like concatenate like a deep learning would be just basically gradient descent on a complicated function. So now you know deep learning. Okay. This is clear. So this mechanics of backward is a little bit confusing, but if you understand what is going on, there's this So what is happening is sort of in like software engineering, they call it like a side effect. So this backward has a side effect. When you apply it to some tensor, it's not going to change the tensor. It's going to like have some effects outside somewhere else. And its effect is like updating the gradient of all the tensors that went into constructing this. And this is a very like impressive thing, because once you start like composing functions, like you get a very complicated function, which is a composition of a bunch of other things. Then when you apply this backward, it's going to compute the gradient with respect to all the things that are in the intermediate steps. So you're going to get the gradient with respect to the original vector, and also like one step after it and one step after it, all the way to get to the final point. And hopefully I'll show this later at some point. This part is because there's going to be a lot of, I'm going to hopefully post this and you can play with it. If you don't do this, you're going to get a complaint, because so this is saying that telling PyTorch to not keep track of gradients in the following, like these operations that go here. Otherwise, this is like PyTorch is going to think that theta is going to be a function of the other side and tries to figure out the gradient of that operation. That doesn't make much sense, because it's like you're doing like theta based on its own gradient. So this is like you're doing your own thing. You don't want this to like be part of the mechanics of calculating the gradients. So you just want to do this and then be done. So you do this so that for this operation, PyTorch doesn't like think that this is part of the gradient calculation that has to like keep track of. Okay, sounds good. So let's do the example of linear regression then. Questions? Let's see if I can get that. Right, so if you remember, there was this empirical loss minimization business. So we had, so ERM. So anyone remembers what the ERM was? Empirical risk minimization in the context of regression, or let's say linear, or let's say linear regression viewed. Linear regression viewed as ERM. Anyone remembers what was the idea here? So regression was minimize over F expectation of f of x minus y, or y minus f of x. We use quadratic loss to define regression. So that was the regression problem for us. But we couldn't calculate the expectation. So instead we have a training data, which is x1, y1 up to, I'm going to do a small x here. It's common. So for training data, you're going to use small. So how can I approximate this optimal regression function argument? So what was the idea of empirical risk minimization? Anyone remembers? Why did we get to optimization actually? So I can't calculate this because I don't know the true distribution, but I can approximate the true distribution, right? So I can say I'm going to try do argmin over f 1 over n summation I from 1 to n yi minus f of xi squared, right? That's what empirical risk minimization would do. But if I try this, so everyone is happy with this. This is like just replacing the expectation with the empirical average over the training data. Okay, so this is replaced by the empirical average. if you recall. But if I try to minimize this, what would I get over all functions? If I try to minimize this loss over all functions, is it going to be a problem? There's going to be a problem. The class of all functions is too big that I'm going to interpolate perfectly. So I'm going to pick an f that matches xi exactly to yi. So f of xi would be yi, and there are many choices. So this is going to give me 0 training error, and there are many choices. So this is not going to be useful. It's one of those non-useful like interpolating estimator. So it's undefined, so I have to define it arbitrarily elsewhere, and this doesn't give me any clue how to define it elsewhere because all of those would have 0 cost function. So this is not going to be helpful. So instead, what we do in this ERM idea is that we're going to restrict the class of functions over which we optimize. So in linear regression, you're going to define the class of all f that are linear. So f is linear. And so this class would be equivalently like represented as like f theta, where f theta of x is theta transpose x for some theta. Okay, so if I restrict myself to the class of all linear functions, then what I would get is a well-defined problem, because then this class is sufficiently small that I can't necessarily achieve 0 training error. And there's going to be an interesting sort of unique solution. This turns out to be with this set of choices, this problem would be linear regression. So equivalently, if I minimize this, I can minimize over theta. So this would be argmin theta in RD. And then 1 over n summation I from 1 to n. I'm going to plug in here the form of the f. Right, and then once I get theta hat, my estimator would be f hat is just f of theta hat. So that's just this linear function with the theta hat there. Okay, so that's what you get when you do ERM in the context of regression. If you do regression, sorry, if you do ERM with the linear class, you would get this, which is linear regression. Okay, so if you recall, this is equivalent to theta hat being argmin 1 over n y minus x theta norm 2, where y is collecting all these responses or targets, and x collects all these x's. So these are the features. So this is going to be n by d. This is going to be n by 1. And this would be my regression problem. So from ERM, you get to this formulation of least squares. I encourage you to go through this calculation. So this is exactly that when you write it in vector form. Okay, hopefully people know this from a regression class. All right, so this should be familiar, right, from 100C or elsewhere. But this is really this version, and this version, like least squares version, is just ERM or a function class which is linear. Okay. We talked about this last time, so I'm not going to spend too much time on it. Just remind you that that's the optimization problem now that we want to solve. Sounds good? Theta in RD. So I'm going to solve this, which is which you can solve by taking the derivative with respect to theta setting equal to 0 and solving that give you the normal equations. Usually like invertible, you get the closed form solution. But I want to do it with gradient descent so that you can see it's very simple to do. Sounds good? So what I'm going to do is I'm going to create yi's that are from some theta star transpose xi. So I'm going to assume that, oh, right? So there is this true function, which is f theta star, which is going to be theta star transpose x, right? And then yi would be very noiseless problem. Right? Yi would be exactly f applied to this, which is going to be theta star transpose times xi. So I'm going to create this data. There's no noise. Okay. And then my training would be just xi, yi's. I'm going to solve this regression problem with this data. And hopefully we should get back theta star or close to theta star. Right? So usually you generate something like yi is equal to theta star transpose xi plus noise. I'm just avoiding the noise here. If this is like this, then the true regression function is really this, you can verify. And if you have a noise here and noise is zero mean, then expectation of y. In general, this is going to be theta star xi. So this is really the regression function if expectation of wi is zero. And wi is independent of xi. So in any case, we're going to generate this. Okay, so that's the plan. See how gradient descent works. And learn a little bit more about PyTorch. So how do we create? Let's see if we can do this. Let's say train is 50. So we can create random data sets of size and train times 2. Okay. Random data set size Gaussian entries. Okay. So it's going to create a design matrix like this. So this is random normal. And you can see it's just, so this is our design matrix. So 50 by 2. So each row is one of these xi's. Okay, and then I'm going to do y, which is going to be this, right? So y would be just random. This is not going to work, okay? This is really not useful. If I do this, because they're like completely independent, that's not going to work. So theta, say a star. Okay, so 1, 2. And then y would be x. Okay, so just doing this. So this is also tells you, okay, no, that's one. So this is x times, this is like x matrix multiplication is at x matrix multiplication with theta star. So x is 50 by 2. Theta is like a 2-dimensional vector. And then I don't want this part. This part is the noise, which is, we don't do noise here. I don't want to do noise. Yeah. So you can see like creates a vector, which is 50 by 1, or like 50, not by 1, just vector. So that's the real like training data. So x and y is going to be a training data for us. Okay. So each row of x, so basically like y0 and x, this would be the first row. Like this, the first, and then the y1, and this would be the second one. Okay, so these are my regression data. So how do we do gradient descent, I have to redefine the loss. So where was the loss here? Right, so this was my loss. I'm going to redefine it. How do we redefine the loss? So define a quadratic. Let's see if it understands. Okay, not bad. So what this is doing is like x times theta minus y. This is to the power 2, and it takes the mean. Okay, so what this is doing exactly what we had here. So loss would be basically, so x times theta minus y, right? And then I'm going to take the norm. Basically, what it's saying is that take the ith element, square it, and then take the average, which is something like this. So that's what it's doing. See if it works. So it's going to be yeah, the remaining, okay. Right, so this is the way that it calculated it. So an alternative way is just what I wrote. So you can write it as norm x theta minus y. So mathematically, they're the same. So the norm squared is just this summation. So x theta minus y. And so that's the loss. I'm going to copy paste this here now. Okay, so PyTorch we can also do. Let's see what happens. Have this. Let's hope that there's no error. Okay, so that's exactly the gradient descent. I just changed the loss. You can see the loss is there. The rest of the step I just copy pasted. The only thing that I changed is here, and this theta is going down, and it's getting very close to 1, 2. So 1, 2 was the true theta star. That was the theta star, right? So if I maybe copy paste this as well, let's see what we have here. But the loss. So this shows the loss, right? The loss is going down. And what I want is something a little bit more fancy. Maybe here. Yeah, okay, so this is the picture that I want. That what happens if you take a step which is too large. Okay, so when you take a step which is too large, you move, but then you correct, and you move and correct. And then if you take too much, like you want it to come like this, but when you take the step too large, you're on the other side, and you have to move back, you have to move back, you have to move back. And if you take a very large step, this is the same setting, but just a better version. If I do like 1, you can see that, yeah, so you basically go to infinity, so it doesn't show up, but you can see that the scale, like 1 to the 18. So this didn't converge. So it started, so moved around, and then eventually went to infinity. So the step size is really critical, and you can see the loss just blows up, right? So there's a critical step size here. It's like around 0.7 you still. So if you take the good step size, you're gonna move, but still, yeah, still not good, 0.7. But if it's too big, then you're not gonna, yeah, you can see it's going down. If it's too big, you're not gonna convert. So you want like a balance. So this is gonna be tricky, but we can see basically you can do the regression. And the only thing that changed here is just I redefined the loss. So now you can have a very complicated model. As long as you define the loss, this gradient step hopefully tries to minimize. So these are convex functions. You can see the level sets are very benign. There's no other like stationary points or local minima. You're just going to converge. Like if you don't do too many crazy things, it's going to converge. For more complicated models, the loss is going to be a little bit more interesting, but the mechanics are sort of simple. So next time, hopefully, I'm going to come back and do a bit of logistic regression.